Now we're going to be talking about 9.2. Before we talk about 9.2 though, just as a bit of fun, I went and dug up one of the oldest pieces of code that I've written, and it's from one of the oldest. It'd be one of the oldest. This is from 2009. This would be like just one of the very first times I ever tried to write something that worked, and it was a find a word generator. What's a find a word again? That's what it's called, but I totally forget what a find a word is. Oh yeah, yeah. It was like I think I was like very young, and I was like, wouldn't it be cool if I could take in a list of words, like 10 words, and then put them all randomly in a find a word or something, and like an easy option they wouldn't overlap, and a hard option they'd overlap, and I was feeling very ambitious. But if you wanted like an example of like accidental complexity, it's like this is written in a language called PHP, but like I always just have this file in my mind because every time I kind of glance over it, I remember trying to. I have no memory of writing this code, but it's like I see this and I'm like, wow, okay, well, this is an example of accidental complexity or even poor design, right? Because like just bad variable names in general, that's pretty obvious kind of stuff. But then you go further down and you start to see, you get loops within loops. This you could argue is accidental complexity because there are ways to do this, right? Like in Python, you have list comprehension, so you don't need to sometimes do loops and loops to set things by defaults. Look at the size of this particular function, like for loops, if statements, do while loops for God knows what reason, if statements, for loops, if statements, else statements, if else, if for, if. Like this is like kind of what to this day, this is what I think about when I think about accidental complexity. Because could you imagine if like, this is what I'll do, I'll put this in the exam and say, here you go, calculate the cyclomatic complexity of Hayden's moronic work, right? So yeah, this just comes to my mind and I thought I'd share it because it's just such an easy example. Like, look at this nonsense. Look at this for loop. Like, I don't know if you remember or how many of you know this in C, but it's like in a for loop, it's not just like to do C, it's not just like for int I equals 0, I is less than 5, plus I or something, or I plus plus, you're probably more familiar with. You can actually add a lot more stuff to all of these conditions. You can actually say, yeah, I want to make int j is 0 too, and I want to make, I don't know if you can do it like this, but and then I can say, it's not just I plus plus, nj plus plus, nk plus plus, and it's like, this just starts to make your code messy, right? Starts to get ugly as hell. So that's actually what's happening here. Is again, this is why I love talking in these courses, because this is young programming stupidity, right? It's like this is that stage where someone thinks they really are good at what they're doing and they're not, right? Because it's like, let's set up this variable, and they're not even like default, so it's literally saying let a equals b and c equals d, and yeah, it just keeps going, and there's just kind of crap everywhere. So it worked probably. Sure, we could try and run it. That'd be tonight's project. See if I can run this old thing. So anyway, that was a quick tangent. So sorry to start a lecture about software safety on, like, the first 3 minutes of that being about the previous complexity lecture, but that's okay. I doubt anyone's like, I'm going to go watch this exact safety lecture because I'm super interested. So point today is talking about safety and type checking. Why are we discussing this? And why is it labeled 8.2? Sorry, I'll fix that up. That should say 9.2. That's just a typo. So in this lecture, we need to be able to understand the characteristics of programming languages and approach in terms of how they may prevent bugs. Learning about different languages is really cool. You've probably gotten this from working with C, right? Working with Python after working with C. You're like, Python, I don't have types, and like I can do this and I can do that, but in C I could do this, and I really miss that, and I miss compiling, and like blah blah blah. You probably got lots of different things going through your head, and being able to understand the characteristics of programming languages is really interesting, right? You're going to go do Java soon. You'll go learn other languages probably throughout your course. Either you'll be taught them or you'll be expected to teach yourself them. However, the key thing we're talking about today is the different characteristics of programming languages in terms of software safety. So like this is like the safety that the software provides, right? What the hell is software safety? Well, we're going to talk about that. But in general, we're going to talk about software safety, memory safety, runtime error safety, type safety. So let's chat about safety, software safety. So what's the difference between safety and security, right? I'm sure you don't know. You ever had this conversation with your partner? Be like, you make me feel safe, but I don't feel very secure, and they're like, what are you talking about? Don't have that conversation. It's probably a weird way of phrasing it. But in the world of software, it's like you have these two kind of key areas that we talk about, which is safety and security. Now, most of you have probably thought about security, right? Software security. You get it, okay? You don't want people to hack you. What is software safety, though? So software security is protecting software from deliberate misuse. That's trying to stop malicious people, people who are trying to do you harm, to take advantage of things. There's some great security courses in CSE, and we often talk about that in the world of cybersecurity. You have software. If it doesn't work, that's a bug, and if that bug can allow someone to take advantage of your software, that's what we call a vulnerability. And if someone takes advantage of that vulnerability, it's what we call an exploitation, right? So there's these kind of layers of how we think about cybersecurity, and there are courses that go into a great deal of depth on this stuff. But all of that is, again, it's about preventing exploitation. Because to prevent exploitation, you want to stop vulnerabilities existing, and vulnerabilities come from bugs. So that's security. Software safety, though, is protection from accidental misuse. It's trying to protect it from you, right? Because you're the dangerous one here. No one's out there to destroy or take down your UNSW Screams application. No one cares, right? It's just you're trying to protect your code from yourself, from accidental misuse. So that's what software safety is, protection from accidental misuse. Software becomes unsafe when it's either designed or implemented to allow unexpected or unintended behaviors, basically bugs, right? And typically during runtime as well. So you write software that you think works, but then it has bugs during runtime. Now, bugs come in all different shapes and sizes and forms, but kind of common ones that you'll see that can be particularly bad are in C, reading uninitialized memory. So, if you ever compile with GCC, you'll know that you can access memory that's out of bounds. You can try and access a null pointer, get the data at a null address. You can try and use a file that's been closed. There's a whole bunch of things you can do. And if you do all of these things, you are, or if these things are possible, you would say that your software is less safe, because safe software should not be allowed to be accidentally misused, right? So maybe you think about it like, it's like a defensive programming or preventing bugs. So for instance, when you have an array of 5 items and you have a function that lets you get a value from that array, you can maybe put a check in to require that value is the value, the index entered is between the two bounds. That's how you can make your software safer, by preventing accidental misuse. Because if you make your software safe, then someone shouldn't be able to accidentally do something dumb with it, right? Now, a really fun fact, this I didn't include this in the original slide deck, but I do love it. Rob, you don't know Rob, but Rob found it. It's like around 94% of spreadsheets contain errors. And what that means is that, when you look at when someone did the research on this, it was like, you look at every formula you've ever written in, Microsoft Excel or Google Sheets, there's a 1% chance it contains an error, right? And I don't mean an error that, says error, like an error that's just giving you the wrong value. Now that's kind of crazy, right? So this software is not safe. There's bugs everywhere. We've talked about bugs. We've talked about verification. We've done this in detail. But let's actually talk about a couple of different issues around software safety. So the first one is, this is just a recap. You know that there's ways we can make sure software works statically with Pylint. We've been talking about that. And there's ways we can make sure it works dynamically. Or more specifically, there are bugs that can, kind of happen statically, and bugs that can happen dynamically in runtime. For instance, if you have a program that has, again, a list of 10 items, and you scanf or you, get line or something in from, or argv in some data to say what item do you want, you can't, at compile time, ensure that that's safe. You actually have to have code that makes that safety, makes the code safe at runtime. In terms of the static part, in terms of removing the errors statically, you have lots of different ways to get around this. And again, what errors are we talking about? With, you know, out of bounds, null pointer exceptions, all of this. Static errors are removed by either compilers or linters. So for interpreted programs like Python, we use pylint to statically detect certain errors. For instance, you know, again, unused variable. Like, you can write Python that uses a variable that hasn't been defined, and it will try and run, I think. I can't remember that. I don't do this much, so let me just quickly sanity check. Blah.py. Oh, sure. Will it actually run? It's hard to tell because Python kind of compiles. No, it crashed. It ran. This is an exception. So the program ran. It didn't do anything. Whereas like Python will do some stuff before it runs sometimes. Like for instance, if you have something like this. But I don't think syntax error is actually is syntax error an exception? Sorry, I'm just discovering things now. I don't think syntax error is an exception. Pretty sure syntax error. This is like Python doing a little quick compile before it runs, right? I'm pretty sure. So there are things that like Python still kind of does some compile-y stuff, but unlike C, if you have an undefined variable, like if you just use hello2, Python's not going to pick up on that statically. We rely on linters to do that for us, right? Hello2 is not defined. This was actually done at runtime. And if we pylint blah, it's probably not, is it going to tell us? Probably tell us, right? Undefined variable. So all of this, again, is around trying to prevent accidental misuse, because for all you know, again, what happens if your code, for instance, has this kind of if statement that's like, if the year is greater than 2022, we want to print hello2. What do you notice about this code? Not year, sorry. Year equals 2021, or I could use, you know, datetime dot, how do I get the year in Python? Is it datetime dot now dot year? Is that it? Import datetime. I think that's it. Because datetime. Well, in the datetime library, you have the datetime object, which you can access the now method on it, which will give you the current, like a datetime object for right now, and then a year is a property on that. So that's how we get this. But you notice this code works, right? So when we talk about accidental misuse, there is a bug in this code that you are not noticing because you have not set the year correctly. So now this code is set up to basically kind of crash later on. And similarly, if you think about other bad ways to write code, you might have a function up here, say, called like add two numbers, 1 and 2, that simply returns 1 and 2. This is a stupid function. And then down here, before you actually print hello, you might say add, I want to add, you know, my, I don't know, add a number in a test in for 4. You can't add a number in a string in Python like that. But again, this code will work. Will pylint pick up on this problem? No. It did not pick up on the problem, right? And I'm just kind of alluding to some stuff we're talking about here today, but it's like, you can see these are all ways that your program could have bugs or deal with accidental misuse. So we can try and remove errors statically, though there are limitations of that, of course. C, the compiler is very strong and very powerful. It detects a whole bunch of stuff, including type errors. In Python, we use pylint. We've just kind of covered that. But let's actually get into the types of errors, because that's really what I want to talk about today. So what kinds of things can go wrong in these different languages? You know, what are things that can go wrong in C that are very hard to kind of, you know, prevent and make sure your software is safe? Well, there's reading from memory that's not been initialized, dereferencing null pointer, using memory that's been freed, writing outside the bounds of an array, and forgetting to free allocated memory, like a memory leak, right? All of these can introduce bugs and create some strange things. What's wrong with Python? Well, what can you do wrong in Python? Well, you can access a variable that hasn't been initialized. You can access memory that an object doesn't have. You can pass in a function of type object it doesn't expect. Now, we actually demonstrated the first and the last one just there. We accessed a variable that hasn't been initialized, hello2, and we passed a function of type that the object doesn't expect. So our add function did not expect me to give it a string and a number. It expected me to give it two types that it could add together. So there's lots of these different types of errors that can kind of go wrong, as you know, in these languages. But a few key categories of errors that I want to talk about include memory safety, number one. So memory safety is a problem you notice in C more than anything. You probably haven't dealt with memory errors in Python. And memory safety is the topic around protecting bugs relating to memory access. Sorry, I just found out there's a bowl on the ground for some reason. Memory safety is protecting bugs relating to memory access. So Python is memory safe because it prevents you accessing memory. You can't, like, Python uses pointers, kind of. Like, Python uses language like C underneath to make things happen. So Python uses pointers. It mallocs memory somewhere, but it hides it from you. And because it's so robust, Python is memory safe in that regard because you can't make a mistake there. Most of the checks Python does are at runtime. So for instance, how do you think Python frees things? Well, Python just figures it out. That's why Python's slower, right? Because in C, you malloc some memory and then you go and free it when you're done with it. And in Python, you just make a new object and Python will malloc that for you quietly, but then it'll wait till it sees that you're not using it and then it'll free it, right? So doing all this kind of checking for you is what makes it kind of slower. So in terms of memory safety, Python's very, very good. There is a cost to this memory safety, of course, but we consider that a negligible cost to the massive benefit of, Python checking more stuff for us. And it's not just about mallocing and freeing, right? It's also about lists. Like in Python, if you in C, for instance, write a program that does something like this, where you say, list equals 1, 2, 3, and then you say print list 4, what will Python do? It'll give you an exception. Index error, index out of range. This is Python being memory safe by having all this kind of under the hood stuff running and checking this stuff for you. In C, it would just do this because in C, it does what you tell it, right? Which is why it's fast, but potentially risky. So, C is not memory safe. We don't consider C to be a memory safe program. This is a lens by which you can talk about programming languages. Is C memory safe? Is Java memory safe? Is Python memory safe, right? And C is not memory safe because it doesn't do bounds checking. It doesn't check if pointers are pointing to valid memory, right? Like in C, you don't say dereference this pointer and then C goes and says, I'm going to go check if that's null first and then I'm going to access it. Because the philosophy of C is that performance is more important than safety, right? Is that a bad thing? I'm not saying it's a bad thing. It's just a thing. There's lots of stuff written in C that you wouldn't write in Python because C is very kind of simple and powerful. And for performance systems, you really need that kind of. You don't want memory safety because memory safety is costly, cost time and energy for your software. Beyond memory safety, we have like dealing with runtime errors and the safety associated with that. Because again, in C, you have lots of other things that can happen, like dividing by zero. Dividing by zero is a good example because the compiler will pick up on that. So if I take a step back here and we jump into like C, and I create a file called blah.c, right? Int main, and it returns 0, and I say something like, int a equals 1 and int b equals 0, and then I say printf, a divided by b. So we're dividing by 0 here. And then if I try and compile this particular C file, what happens here? Well, I didn't include std.io, sorry. This compiles, right? And then when I go to run it, floating point exception. Now C's smart enough that there are some certain things in C that this is an example of how C deals with these errors, maybe not gracefully, but it tries to add some level of software safety to accidental misuse because this is you accidentally misusing the language, right? Now, again, this probably comes at some kind of performance cost too, maybe. I'm not too sure. Floating point errors are pretty easy to check, no doubt. You just check if the divisor is 0 and then you go with it. But you have ways to prevent this too. So for instance, if you compiled this with DCC, pretty sure it would detect it. Oh, it doesn't. Okay. Or it would detect it at runtime, right? So this is an example of, runtime safety checking, division by 0, same kind of thing. But back to it, it's like, which one is safer when it comes to handling exceptions? Is it Python or is it C? Well, you'd probably say Python because of the fact that Python relies on exceptions. And in fact, many languages rely on exceptions. C is probably one of the few popular programming languages, imperative programming languages that doesn't rely on exceptions. So in Python, when anything goes wrong, it's typically thrown as some kind of exception that you can catch. And what that means is that in Python, you're largely guaranteed that if you're willing to catch errors, then nothing will kind of happen that isn't expected, right? So C doesn't support exceptions at all, so errors typically have to be included in the return value, and if anything fatal happens, it's very, very difficult to recover from it. And what this really splits you up in is two different types of, I guess, like programming paradigms. And this is, again, really important because you have to have a different mentality when you're programming in C to when you're programming in Python. Because in C, you need to go a lot further to ensure that your software is safe. In Python, the general philosophy that's followed is the easier to ask for forgiveness than permission. You've probably heard the phrase, seek forgiveness, not permission. And what that means is that in Python, we have a tendency to just try and do something and then get ready if it doesn't work, right? So, it's kind of like, I don't know, I don't really have an example for you, but yeah, if you're doing something you're not sure you should do, like, you're playing tennis on a tennis court when the gate was open and you don't know if you have to book it or something. It's like, you can just kind of go in and play tennis, but you got your shoes on ready to run away so you don't, get attacked by the tennis court owners or something. That's you kind of seeking forgiveness, not permission. You're like, let's just do it, and let's just be wary something bad might happen here. That's kind of the Python approach. Now, the benefit of that is that it simplifies a lot of your logic. It makes code a lot easier to read. The downside, though, is it makes your code not structured and harder to reason with. Because a lot of exceptions, like you think about cyclomatic complexity again, that all made sense when we had these like nice little if and while statements. But could you imagine if you had like a function that then calls another function and calls another function, and then there's an exception that might bubble back up? So it makes it really hard to kind of reason and flow through code. That's one big downside of it. But it does make the code kind of easier to deal with. So this is like Python's way of trying to make your software safe and bug free. The kind of C style way is the look before you leap kind of approach, which says that the only time you do something is if you have established total assurance that you can do it. Right, so back to the tennis example, it's like you don't hop on that court until you have checked that you can and you should and you're allowed and nothing's going to go wrong, and then you hop on it and you don't look back, you do it. And this is like this, like we do this all the time with in C, right? Like you've probably seen this where if you want to dereference something that could be null, like in Python, if you had some, I don't know, let's say in Python you had some pointer, like int star a is null, you might just say like, yeah, printf %d. This is going to be some weird hybrid, but you'd be like, try, we'll just do that, and if it fails, we'll just like catch it, null pointer exception, and we'll just say, yeah, like whatever. That's the seek forgiveness, not permission approach. Whereas in C, your approach is going to be very different. You're going to say, if A is null, or I should say more specifically, if A is not null, then we're going to printf here like that. So that is the look before you leap, because you want to make sure that by the time you hit that printf, that everything's been checked and good. And this is important because the inherent checks to ensure your software is safe in C are much less, right? So C is not going to check this for you. It's just going to do it. It's just going to say, hey, you told me to grab that value at that address. I don't know what it is. I'm going to do exactly what you say. Like, we all know these people, right? Like, what's that old joke where someone's like, this is totally unrelated, but someone's like, can you run to the shops, get me a dozen eggs and flour? And someone comes back with 12 eggs and 12 bags of flour, because they're like, oh, I just did what you told me. You're like, damn it, that's not what I wanted. I wanted you to think a bit more. I wanted you to, to check, apply some logic here. Because, like, C will do some pretty stupid things, right? Like, this will probably work. GCC blah.c blah. Like, why did it do that? It should, like, you're like, don't you know you can't do that? You have all the information you need here to not do that, but it doesn't. And that's just a different type of programming language, which is why back to the start of this lecture, we said it's important to understand the different characteristics and apply words to it, And I understand a lot of you get this, right? Like, there's nothing profound in this lecture. Like, you're not like, whoa, yeah, you're right. Python doesn't check memory. You probably figured that out the day you got excited that you don't have to free things. The point of today is just to try and put some words on it, put some conventions on it again, so that you can actually talk about it and put it in a context. So back to handling runtime errors, look before you leap. That's the C-style approach. The good side is it doesn't have exceptions, which makes code easier to reason with. The downside is that you often have very obscure logic because you often have to do tons and tons of checks as opposed to just do this and catch an exception. Because isn't that like a nice thing about Python sometimes, is you can just say, yep, open this file, and if anything goes wrong, just make a new file. You can't really do that in C. You kind of have to, you'd be like, oh, I got to check, does that directory exist? And then, maybe does that file exist? And then I open it and be like, is it of the right encoding type? And, your core logic can get obscured by other checks in your code. Okay, so onto the last, I guess, part of this, which is type safety, which bleeds into the last bit of the topic. Type safety is a massive, massive topic in itself. Type safety is preventing a mismatch between the actual and expected types of variables, constants, and functions. Why do you think in C that you use ints and doubles and whatnot? Now, it's like, yes, the computer needs to know what you're passing it because it's got to allocate memory, right? Because ints are different size to doubles and different size to chars. While that's true, you could argue for many languages, why don't like chars are 1 byte and ints are 4 bytes and doubles are 8 bytes. Why don't you just store everything in 8 bytes? Right? We have so much memory on computers these days anyway. Like, why don't we just store chars, ints, and doubles all in 8 bytes of memory? Therefore, the compiler doesn't need to know what size it is because everything's 8 bytes, right? You just say list. You just go Python style. You just, yep, number this, that. It just stores it in whatever you want. The downside of that, though, is you're eventually going to make a mistake. You're eventually going to make a mistake like what we did in our blah.py file, wherever that is, where we actually made a function called add that took in 2 things, and we gave it 2 things, but what it expected to get was not what it actually got. So types aren't just about, this, they are about actually allowing the computer to run your program in terms of memory, but they're also about trying to make sure that you are using your software correctly. In a lot of ways, type safety is probably the biggest topic around software safety because it prevents so much accidental misuse at runtime, it's not even funny. So C is type safe, which means that types must be declared and the compiler will check that the types are correct. And you know this because if you have a function that takes in an int and a double and you try and pass it in something that isn't compatible or can't be implicitly casted to that type, it will just crap its pants and it will say, no, I don't want that, and it'll happen at compile time. It will happen statically before the program even runs. And that's great because the more that can happen statically, the better. Whereas what happens in Python? It doesn't happen statically. It doesn't happen by the compiler. It happens when you run it. So, if I run my Python 3 blah.py, oops, let me just fix that up. If I run this, it works, but then if, say, the year suddenly becomes 2021, everyone always looks at me so funny. There's like a window. I told you, there's a window outside and there's like a drive. People always like walk past and they just look in and they're like, why is he yelling at his computer? So now when I run this, right, sorry, this is meant to be like 2023 or something. The add function will crash, but what's happening here is it's crashing at runtime because type error is an exception. We don't like dynamic, like software safety checks. We don't like dynamic type checks because now the program is not behaving correctly. Now, yes, you could catch that, but what if you didn't catch it, right? And also, like, things at runtime are so variable based on input, so the more you can get certainty statically, the better. So this is where one area where C really shines out above. Now, Python on its own is not type safe. You know this because you don't declare any types. Everything has a type, but that type is not known until the program is executed. Is this a good thing or a bad thing, right? That's a question for you to think about. Do you like it or do you not? Do you like the lack of type safety, right? Do you find it's easier to program or harder to program? Now, I think it's a super interesting question. From what I can tell, languages that are what we call loosely typed or don't have much type safety became really popular this century because they made programming really fast to write. Like, I mean, think about the crazy things you can do with Python in like 5 minutes. you can solve very complex problems. Like your group allocations for your project, some of the auto marking and leaderboard stuff, that was literally I did your groups in Python in about 15 minutes. Input this, input that, list this, loop, 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 just shove it all together because the language is so light. If I was to do that in C, it would take me like literally a few hours. Be like, oh, I gotta, whatever that function is, the one that copies it, string copy. I gotta like string copy in from the file into some memory, and then I'm like, I have to malloc it, and I'm like, it just, it'd be like really hurt my brain. So there's some big advantages to it, but one of the downsides of it is that you've probably made some errors. I don't have a preference. I'm probably not going to give a preference, but it depends what you're doing. But who's had this experience where you start writing Python and you think, cool, okay, this is all working fine, it's nice and simple, and then you start to write more complex projects, and then suddenly you run into that problem, which mainly comes up in the area of functions. You are passing a function what it doesn't expect. Now, here's what I mean. If you think about a language like C, for this project, we could have given you the structs. Think about the data types in the spec, right? We could have given you 6.1. We could have given you the data types here. Workspace stats is this, which is a list of this, and blah, blah. Like we could have actually made these structs for you and disseminated them to you as well. You know how cool that would have been if you were writing this in C? Because if you weren't returning the right types, if you weren't returning the right things in the right areas, the compiler would find that out for you before your code even runs. It would be like, hey, there's a problem here. And you'd be like, damn, you're right. Thank you. I wouldn't have found that. And you think about some of the woes you've had with Python so far, right? Where you think you've done it all right, but it turns out this is actually a string when it should have been an int, or like this is a dictionary when it should have been a list of dictionaries, and all of that stuff, because you're passing in the wrong things and returning the wrong things, because Python will take anything as long as it can validly deal with it, right? Like Python doesn't care if I'm adding together strings or numbers, right? If I do this won't crash. Well, it'll crash on the hello 2 part, but it's not crashing on the concatenate part because Python's like, yeah, just give me whatever you want. I'll try and add them together. I'll add whatever you want together. If it doesn't work, it doesn't work. That's the kind of attitude for it. So the downside with languages with poor type safety is that typically as the projects or the work gets more complex or it scales up, it is it's just more costly and complicated. So I was just getting an error. So back to Alex's, do people ever write an entire project in Python for fast development and then rewrite it in C to make it more reliable or fast? Not really. You'd probably really screwed up. Like if you're writing a project that should have been written in C, like there's not really an overlap. Like you'd never really be like, I'm going to write this in Python then written in C. Like, I don't know how to put it. You'd know before you go into it, right? Like no one's being like, I'm going to go and write like sometimes, I don't know, not C. Maybe that's the best answer I can give. Not C. Maybe C++. Maybe Java or C# or something, but not C, because like C's capabilities are just very different. Like you could meaningfully convert some programs from Python to C++ with X units of effort, whereas like converting it to say C could take 10x units of effort or something crazy. But back to the point, we have languages that have non-optional built-in static type checking, right? As in you have to use them. C, Java, Haskell. You have languages with optional but still built-in static type checking, like TypeScript and Objective-C. So these are loosely typed languages that have type checkers built on top of it that, always works, but you can turn them off. And then you have languages which you can use type checkers, but you have to kind of install them externally. And that includes Python and Ruby. that's where this last bit, mypy, comes into it. So mypy is a type checker function for Python, right? And what that means is that mypy will check Python types and help you kind of interact with it like it's C. It allows you to give variables types like it's C, and then mypy will statically check it just like Pylint, right? So it's not a dynamic thing. Most type checking is not dynamic. Like most type checking, C and all these other things, Java, they all happen before, like it uses that to compile, and then what's compiled has certainty it works. So these are all, static analysis tools. Now, here is an example of some code. We actually have this up in 9.2. Yep, 9.2. My head's in the way. Even I can't see it. Oh, there it is, over there. Ah! Why isn't this working? Oh, okay, cool. Safety.py. Right, so what I've got here is I've got this file called safety.py. Now, it's basically a VLab's tiny. There we go. It's basically just like a count and a search thing where you give it a list, which a string is a list of characters. So you give it a list like hey hen, and then you want to count the number of times that h is in that list, right? Now, this is all well and good, and this program should work. Python 3 safety. Yep, 2 and none. This makes sense. So how many times does h appear in it? 2. How many times does z? Well, can you find z in there? No. What happens if I make this one h? It should return me like with h. So what this program actually does here is like count just goes through and counts how often it exists, and search just returns the value if it exists, otherwise it returns none. Now the problem with this kind of thing is that I can do something like put a 2 here, and this will still work, right? Because in Python's very comfortable checking things are, is this string match this integer? It's like, yeah, I'll check it. Might as well check it. But that doesn't make any sense. This is an example of like software not being safe because this is you accidentally misusing it. This is you using it how it shouldn't be used. Not intentionally. Maybe you have good intentions. Maybe you want to check if my name actually has a 2 in it, but like 2 the string. Because that'd be valid. Do you want to check if the character 2 is in my name? No. But how do you get around this? So what we do to like solve this problem, and this is the mypy doc. So we can actually go to mypy's website here. Now mypy was installed as part of the requirements.txt. You can go and pip3 install it yourself. But the simple example here is that here is a Python function, and you can statically type, particularly function parameters and function return types. That's the most common kind of place to do it because most of your type errors happen in functions because it's pretty hard to, well, it's not hard, it's a lot easier to tell if you're doing something wrong within a function because you've got the whole thing there. They're all local variables, but like functions are hard. Like I'm sure in your project you might have a function like message send which takes in an object with like 4 parameters or something, and it's like, do you ever have a moment where you stop and you're like, what the hell does that take in again? And you have to go and look at the other file to remember what it takes in, and then you try and send the right stuff in, but it's wrong, or even worse, it might be wrong but you can't tell. So that's why we care a lot about function stuff here. So what we can say is that, well, here my count function, I have to import, do I have to import typing? Yeah, I think you have to, or you don't have to import typing for this. So the way mypy works is that it kind of like interprets your Python code, but it expects some extra characters, I'm pretty sure. So it's like if I get rid of that import for a second, what I can say here is that I expect my needle to be a character, which I think is char. Let's just look it up in the docs because I don't do this every day. It's probably all written down in a really obvious place. Installing more function signatures, additional types, function signatures. Why not? Char. Let's just look at char. Oh, string. Okay, maybe they don't like string. So we've got string there. There you go. Right now, I do know some of this. I'm just trying to show you. You might look it up. So what I say is that my needle is going to be a string. My haystack is going to be a string. Okay, Well, that makes sense. So now let's see what happens when I run this program. Now when I run this program, it still works because it's not like C where the compiler is checking it for me. This is an external tool that's used to type check it. So for instance here, how I actually do this is I run mypy, which is the Python type checker, and I run that on safety.py. Oops. Sorry, what is it? MyPy. My brain is melting. How do I run MyPy? Oh no. Someone will know. Someone here is always installing and running MyPy. Or did I just not install it? Oh, sure. So where is MyPy in, you know, requirements.txt? Is it? Oops. It should be in here, or it's either in the extra file. Perhaps I haven't installed it. MyPy. Okay, so it is installed there. So sometimes this is because it wasn't installed. Like if I pip3 install, and then I give it the requirements file, which is sitting on the CSE server. Oops. Oh well. So this is like where the pip3 install -r is to install those requirements. Yeah. Cool. Bam, 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 bam. Maybe I didn't install it. I might have wiped my pro directory a while ago. And most of our lecture examples don't actually use a lot of Python libraries, so maybe that's the problem. We'll figure it out pretty quick. If not, there's another way to show you to run it. If many of you are working on Windows, you probably have this problem where you install things like Pylint and stuff. Remember, the reason if you have installed it and your operating system says, I don't know what that is, it's because your operating system doesn't know where to find it. So MyPy looks like it works now, right? So I didn't install it correctly. On most machines, if you have installed it and you still get that error, you can run python3-m mypy safety.py. And you've probably done this with Flask already too, right? It's the same thing. It basically uses instead of asking the operating system to find a Python module, you're now saying, hey operating system, you know what Python is. Can you ask Python to find that module? So it's like going through Python to find it, which is like a little bit less prone to errors. So now I can see a safety.py argument 1 to count has incompatible type int expected string, and you're like, oh, there we go, there's my problem. No issues found. You could add this to your pipeline, right? You could actually type your functions and add this check to your pipeline to like do type checking as part of it. And I can specify the return type too. So what's the return type? Well, it's going to return me an int or an integer. I think it's int. There you go. So what this saying is it expects copies to be an int. So MyPy statically analyzes your code. It looks at copies and it says, yeah, it's an int. Loops through it. Yeah, these are always ints. Nothing changes. Nothing crazy happens. But you see if I change this, say, copies equals A, it'll pick up on it and it'll tell me there's a problem. It's like, sorry, you've created a problem there. How do we do the type checking for search? Well, what's our search do? It takes in 2 strings again. Takes in a needle and a haystack. However, what we're returning in this case is either the string itself or it's none. So this is where you actually kind of have to go and read the MyPy library, because you can, and this is true for all languages, right? Like a lot of languages out there, you can create really complex types. I'm just trying to find an example of it. So you can create really complex types such as union, right? And what union is union, it says like one or the other. So what this normalize IDs function says is take in a parameter, an argument called user ID, and its type is one of these two here. So I can actually use this little union thing in my code, like this. Whoa, what's happening? And now I can say that my search function is going to return one of either string or, I think it's none. Is it none? I think that's it. And there you go, same kind of thing. If you just said string, MyPy would be smart enough to figure out that there are some cases where you return none, right? And then similarly, if you just had it as none, it would figure out there are some cases where, you know, MyPy is pretty smart. It'll figure out whatever like a C compiler can figure out most of the time. Blake says, are there any cases where it can't pick up statically, like maybe inputting an object that comes from a file? Well, that's a good question. In most typed languages, you would actually specify what the structure is that you expect from that file. And that's even better because what that means, it says, is that, like, I get what you're saying, right? Like, what happens if someone actually opens the wrong file? You know, like they give you a file that doesn't match that structure. How do you tell that at compile time? It's like, well, you can't. There are some things you can't tell statically. Remember, all programs are variable on input at runtime. If you don't take user input, or you don't open a file, or you don't access a URL, your program should be determinably correct at compile time because there's no unknown variables, right? But during runtime, there are these unknown variables that create these kind of safety problems. So it's more likely, Blake, that you would have a program that has a structure. You would give the type of that particular like object you're reading into, that dictionary you're reading into. It's just that if it doesn't match, you would expect your program to raise an exception, right? So a lot of these things can't be, can't be totally avoided. Okay, I mean that's really it. I mean this again isn't a topic on you have to go and do this. This is more like types are a serious thing in all kinds of languages, and understanding how a language is type safe, how you interact with its type safety features. Some languages have really complex typings where you can go and make tons of stuff. C's not really, I don't think C has a very strong type system per se. Or when I say strong, I mean like it doesn't have a very like easy to use type system as much as like it's kind of easy in these languages to say, it could be one of these two things, which is true. Like how do you do that in C? You got a function that returns a number. Well, what happens if it doesn't exist? You're going to return null? You're going to crash the program? No, you have to return -1 or something. And then it's like, oh, okay, well, this gets very complicated because now you're adding more runtime checks to things too. So, yeah, lots to think about. Nothing particularly to do. If you could leave some feedback for this lecture, that would be really good. We're pretty much at the end today, so we're just going to wrap up now. Unless you all had some questions or anything you wanted to check or run through. Yeah, we're just at the end today. See how much it's raining today. Okay, all pretty quiet. Give you just like another 10 or 15 seconds to answer any questions if you have. I'll to ask any questions if you have them. Cool. All right. Well, thank you, everyone. I'll talk to you tomorrow. We'll be doing some more hands-on-y stuff tomorrow with Git and web stuff. It's all kind of bonusy. The Git stuff might come up on your exam loosely, and it's part of your lab, so like it's worth watching that later, but it's not critical. And yeah, should be pretty fun. So we'll have fun tomorrow. And just last question quickly. Blake says, can you show how we did type checking to the pipeline? I've never done it, but honestly, like the thing is, it's really very similar to Pylint. So like if I was doing it right now, I would just copy this whole thing and I would paste it again and call it type check. And then I would just change Pylint to MyPy. And then I think that would be it, actually. I think that would be the whole thing. So, and it will work on CSE because MyPy is part of that, the runner environment. So it should be, play around with it, if you want to do it and it works, go post on the forum, and love to hear more about it. But yeah, have a great day, everyone, and I'll see you all tomorrow. Some of you tomorrow.